synthesis of glucose occurs mostly in the liver and a little bit in the kidney. So, let's say lactate, that's something that happens very commonly. Lactate goes to pyruvate, feeds into oxaloacetate, goes into the Krebs cycle, through the Krebs cycle into glycolysis, and get back up to the level of glucose. And so you can put that back into the blood. This is one thing that a liver would be doing a lot. You don't have to release it. You could store it as glycogen and do other things, but that's what we're talking about. Swimming upstream against all the pathways we've just been talking about. In fact, you're going upstream mostly through glycolytic steps. They have 7 steps that are shared in common, glycolysis and agents. But this one, it doesn't violate what I told you before. I always told you can have 2 major endpoints of metabolism connected, catabolic pathway going down here, and then you can have synthesis pathways, anabolism going back up. They may share some things, but there's always something different. So there are 3 steps in glycolysis that aren't shared in gluconeogenesis. These 3 enzymes are bypassed: hexokinase, phosphofructokinase, and pyruvate kinase, for the 2 reasons we've talked about before. We talked in general terms before, but here we'll see specific. There's energetic reasons to bypass them, and it sets up a system where you can regulate the 2 processes separately. So here's a path from pyruvate to glucose, or glucose to pyruvate, depending on which way you're talking about. Obviously, flowing downhill here on the left is the glycolytic pathway. We've seen all this before, glucose-6-phosphate fructose. The oxidation, the substrate level phosphorylation that happens when you get to pyruvate. So if this is a liver cell, it's just brought in some lactate, it converts it back to pyruvate, it wants to go that way to rebuild glucose. It's going to skip this step. This was an energy producing step. This was a step where we made ATP. You can't push things uphill. We know energetically this would be an uphill trip to try to go back to glycolysis that way. Instead, notice we insert steps where we invest some energy. 2 ATPs go in. Instead of trying to reverse glycolysis, we put in 2 steps where we're investing GTP and ATP, 2 energy-intensive steps there. And up here, we bypass these 2 steps. This is the energy investment phase of glycolysis. But instead of trying to push that backwards and resynthesize ATP, we bypass the adenylase altogether and just hydrolyze that phosphate off to get free glucose. Hydrolyze this phosphate off to get fructose 6-phosphate. So that changes the energetics. Makes it, we already know that this is downhill in this direction energetically, but by the input of these extra steps here, this now is downhill energetically going back up to glucose.
Do we need to know the enzymes that do these?
Well, you might want to know them while you're spending some time on them. So here's the top 2. We're just looking at hexokinase. This enzyme is bypassed and replaced with this enzyme, glucose-6-phosphatase. These 2 investment phase ones, we're not trying to push it back up to make ATP. We're just cleaving the phosphate off with these phosphatases. And here's why, energetically. If you try to reverse glycolysis, that would be this situation. If you produce glucose instead through the physiological process of gluconeogenesis, you have that situation. This would be the net reaction. You're going to need a couple pyruvates, 4 ATPs, 2 GTPs. You're spending 6 ATP equivalents to convert pyruvate to glucose. The overall delta G for that process is quite negative, negative 37. That's very favorable. If you were trying to push glycolysis backwards, those numbers would be, because we know we only make 2 ATP in glycolysis, so if you try and reverse it, you'd be spending 2 ATPs to convert pyruvate to glucose. On paper, you could write it out that way, but the thermodynamics would be positive 74. That's uphill by 74. That's downhill by 37. So you're investing more energy here, and that makes it possible. Both pathways interconvert pyruvate to glucose, It's just a question of how much energy you're throwing at it. 2 ATPs worth or 6 ATPs worth. So there's